Okay, welcome to Python Programming Basics Week 4. We're going to do basically two subjects in this week. First is an introduction to the pandas module, and later we'll take a look at the idea of classes and inheritance, which is the mechanisms that we need to support object-oriented programming. We concluded last week's lecture with the NumPy module, which allowed us to create n-dimensional arrays of like-typed values. For us, that typically meant two-dimensional arrays of float or int values, specifically float64 or int32 values. Pandas allows us to create essentially spreadsheet-like objects where we can think of each row as having a label and each column as having a label and a data type. So let's go ahead and get into pandas here. Now, right off the bat, I forgot an important detail. If we're going to use pandas, we have to import the pandas module. Let me first import math as M, since we might use math facilities, and I'll import NumPy as NP, and now I'm going to import pandas as PD. These are the typical abbreviations that one uses for these modules. Okay, so one of the two key data types that pandas provides for us is something called a series. You can think of this as being, for example, a time series where you have a sequence, for example, of stock prices indexed by date and time, or where perhaps you just have a list of transactions, a sequence of transactions indexed by some transaction number. To create a series, we use pd.series, and notice that series is uppercase. So we're going to say here S1 is pd.series, and you can give any iterable that you like to create the data in the series. So in this example, we're using a list, 3, 5, 2, 4. As the iterable from which we're going to create our series object S1. And by default, these four values will automatically have sequential integers specified as labels for those values. All right, so when I display S1 by just typing S1's name at my shell prompt, the index labels here are just the integers 0, 1, 2, 3. The specific values are 3, 5, 2, 4, and pandas here is storing these as 64-bit ints as opposed to the 32-bit ints that we had in NumPy by default. That means that in pandas by default we can store huge but not arbitrarily huge integer values, roughly between plus and minus 9 quintillion. All right, so every series as a member has values that you can display. And here I'm shown that the values are an array of int values, and particularly they are int64 data types. There's also this index associated with the series. Range index is the series equivalent of the range function that we've used in just plain old Python. So range index allows us not to have just this list of values 0, 1, 2, 3, 4, 5, 6, etc. We can specify a starting value of 0, a stopping value of 4. Recall that the stopping value in the range function and here in the range index is actually one too far. So our stopping value is 4, which actually means we're only going up to 3. And the step size is 1. Now, the index does not have to be integers. In this next example, we're going to create a series. If I can type, we'll do this. pd.series, okay? Oh, here's a big change of pace. We're going to use 4, 2, 1, 5 instead of 3, 5, 2, 4. Okay. So those are my values. Now, I can specify my index by saying index gets and some iterable of index values. Here I'm using a list as my iterable, and I want to use strings, strs, as my labels this time. So A is going to be my first label, then X, then capital C, then question mark. All right, these are not necessarily intended to be sensible labels. Oops, I had a typo there. But you'll see that the values 4, 2, 1, 5 are stored in that order, and the labels are the labels that I specified in my index. Okay. All right, so s2.values is 4215, s2.index. This time is a specific index, not a range index, because I manually typed in the index labels that I wanted. To access a particular item within a series, you can use some appropriate labels. So let's remind ourselves what S1 looks like. S1 has these default integer labels. So if I say S1 sub 2, that gets me the value of 2 associated with the label 2. S2, on the other hand, if I use question mark as a string label, well, that is actually one of the labels valid for S2, and so I get a 5 back. And it turns out that you can use just plain old integer labels if you wish. So S2 sub 3 gives me back the same value, the same slot in that series as S2 sub question mark. Okay, now it's easy to create a series from a dictionary. What's going to happen here is that the key from each dictionary item is going to be used as a label, and the value associated with that key is going to become the value associated with that label in the series. Here I've got a dictionary of some stock tickers, capital X, and prices. I just made these prices up. I don't know how close they are to reality. X is my nod to local corporations. X is the ticker for U.S. Steel. Then we have Apple, 543. That's in the ballpark pre-split. Cisco, 47.7. There we go. So D1 is my dictionary, and now I can very easily just say, give me a series S3 constructed from that dictionary D1. Whoops, your E's. And there we are. Okay. Now, just as you can search whether a particular key is in a dictionary, you can also search whether a particular label is found in a series. So I can ask whether Apple, well, I have to spell it right, is in S3. What did I do wrong? What did I do? Oh, stupid me. I named it S2 instead. All right, so let me hastily patch up things here. Let me recreate S2. And now I'll create S3 from the dictionary D1.
And I can ask, as I did, whether Apple is in S3. And it is. I can ask whether Goldman Sachs is in S3. And it's not. Now,
In our NumPy material,
we looked at the idea of vector arithmetic and slicing and indexing in NumPy ND arrays. Arithmetic, slicing, and indexing work very similarly in Panda's series. So here I have S1 that we created up above. And if I say S1 times gets a 2, that's going to replace every value in the series S1 with twice its original value. So that does change S1. If I do a divide gets, I'm sorry, I'm not doing a divides gets, I'm creating a new object, S4, which is going to be S1 over 2. Now the values, I've multiplied by 2 and then I've divided by 2. The values will be the same values, but they will, of course, be floats rather than ints because of using division. So S4 contains float 64 values, whereas the original S1 contained int 64 values. On the other hand, floor division, if I say S1 floor divide gets 2, floor division does not produce float results if the values that are already in the series are ints. And so this gets us back to the original int64 values that we had, 3524. Addition of two series is vectorized. This is not concatenation as it would be with a list or a stir. All right, so here we get S1 plus S1. I can use NumPy vectorized math functions on the values in a series, assuming that the values in a series are the correct type. In this case, int or float would be fine. And so here we have a series of the square roots of the values in S1. This, of course, didn't change S1. I just got that square root series back as a result. Notice that we're not using math's square root here. If I say m dot square root of S1, this is going to fail because the m dot square root function only expects one argument value that is either an int or a float. And a series, of course, is a vector of values, not an individual value. Slicing works as you would expect. Here's S1. If I ask for S1 up to but not including sub 2, that's going to give me the sub 0 and sub 1 portion. Similarly, S3, recall, has stock tickers and prices, and I can use integer subscripts in my indexing and also in my slicing. So if I say 1 colon, that means give me all the values from item sub 1, which is the second item in the series, to the end of the series. So here I'm getting Apple and Cisco. Now, if the series has explicit labels, as is the case here with S3, we do get one change of behavior that might take you by surprise. So let's remind ourselves what S3 contains. All right, so X, US Steel, with a value 123.2, and then Apple, 543.0, Cisco, 47.7. If I ask for S3 sub Apple colon Cisco, we're accustomed to thinking of that second index there after the colon as being one too far. But in this case, where I have explicit labels set, the slice goes up to and including that second label. All right, so here I have Apple and Cisco rather than just Apple. If you have two series and you try to combine these things using arithmetic, but the indexes don't match, then any positions in the resulting series where either the first series or the second series does not have a corresponding label, the result of the arithmetic is going to be not a number, which displays as NaN, N-A-N. Let's illustrate this. I've got S1 that has these indexes 0, 1, 2, 3, and now I'm going to create S6 as a series. It's going to be a series of 3 values, 3, 7, and 1. And I'm going to use range index to create my index, but I'm going to start at 2 and go up to but not including 5. Okay, so the values are going to be 3, 7, and 1, and the indexes are going to be 2, 3, and 4. Whoops. I forgot that I need to indicate that range index is part of the PD module, so let me patch that up. All right, so PD.rangeIndex. And now we're good. All right, so S1 has 4 values, indexes 0, 1, 2, 3, and S6 has 3 values, indexes 2, 3, and 4. All right, so the overlapping indexes are 2 and 3 in these series. If I add these things together, S1 plus S6, S1 plus 6 gets S1 plus S6. It works, but when I now look at the result, I see that I have not a numbers for the 3 indexes that were only found in one of the 2 series. Okay, so index 0 and 1 are not found in S6. Index 4 is not found in S1. It's only indexes 2 and 3 that are found in both series. And so I have the correct sums for those 2 labels. I can obtain a Boolean index of which values are null or which values are not null using the pandas isNull or not null methods. So for example, in my S1P6 series, if I test PD is null S1P6, I get told here that indexes 0, 1, and 4 are null. That is null is true for those. The inverse of is null is not null. So I can ask whether PD not null S1P6. And in this case, I get true for the 2 values in S1P6 that are not a number. Since that's a Boolean index, I can use that to select out just the portion of this series that has valid data. S1P6 sub PD.notNull S1P6. And now I just have the part of S1P6 where the values are numbers. Okay, so that's the series data type. Another way of thinking about the series data type is that it's like one column of a spreadsheet. The pandas data frame can be thought of as being like an entire spreadsheet. Actually, the pandas data frame is stolen directly from the R language's data.frame. Each column in the data frame has a name, and there are n rows in the data frame. You can easily visualize that by thinking of an Excel spreadsheet with named columns and numbered rows, for example. One easy way to build a data frame is to start with a dict in which the keys are the column names and the values can be specified as equal length lists or tuples or what have you associated with those keys. Now, each value in a column needs to be of the same data type in the same way that all values stored in an ND array have the same data type. So here, ticker has 4 strings as its values, A, B, X, and G. These next couple of columns, CEO by and return percentage, specify characteristics of these stocks. For example, the CEO for the company whose ticker is A has recently bought stock, whereas the CEO of these other 3 companies with tickers B, X, and G have not recently bought stock. And in the third column here, we have the return percentages of these companies. Okay, so let me set this up. I will get back to you when I have got all this hammered in. Okay, and so now I have my dict D2 defined. And from that, I'm going to create F1 as a pandas data frame. And if I look at F1, I see that by default, I get the row labels 0, 1, 2, 3, as you would in an Excel spreadsheet, for example. And my column names, as I said, are taken from the keys in the dictionary, and the values for each of the rows is taken from the values for each of those keys. All right, so now that we have this spreadsheet, we need to be able to know how to access individual cells or columns or rows within this thing in order to be able to obtain the data that we want to analyze. Retrieving a column is straightforward. You give the name of the data frame object and specify as an index a column label. So here I'm saying F1 sub CEO by. What you get back is a series. As I mentioned, you can think of a series as being like a column of a spreadsheet. Notice here that the name of this series is CEO by. Now, previously, when we talked about series, you may remember, well, you probably don't, but I'll remind you right here. We've got this series S1 with the values 3, 5, 2, 4, and the indexes 0, 1, 2, 3. This series did not have a name, but I can give it a name by saying S1.name gets some string. IMS1 will be our clever name for the series S1. Okay, so each column of a data frame is a named series. Now, if the name of the column does not have any special characters in it, like spaces or mathematical symbols like slash or star or %, then I can simply give the name of my data frame object and a dot and specify the column name as a member of that data frame object. So F1.CEO by here is going to give me the same series as F1 sub and then the string CEO by that I used up above. Now, this will not work for return percent because of the percent symbol, which is the mathematical modulus operator. If I attempt to say F1 dot return percent, I'm going to get yelled at. In this case, I do have to use the subscript notation with the square brackets and specify my column name as a string in quotes. Okay. So that's how we retrieve a column. Now, if I want to retrieve a row from a data frame, I can use the square brackets, but I have to precede the square brackets with .loc. Loc for location, I suppose. So F1 is this spreadsheet. F1.loc allows me to use row labels, and sub2 should give me this row here. And indeed it does. I have the ticker is X, the CEO buy is false, return percent is 12. Notice that that is also returned to me as a series. The labels for the series are taken from the column names of the data frame. The values are X, false, and 12.0. I claimed that all of the values within a series have to be of the same data type. So in this case, through the process of so-called upcasting, the string, the Boolean, and the float are all just treated as objects within this series. And the name of this series is just its label 2. Okay, so we now know how to access an entire column by using the column name. We know how to access a particular row by using a row index with .loc. You can combine a column name and a row label in various ways to access individual cells within the spreadsheet. So F1 is our object. If I say F1 sub CEO by, that we know is going to be a series for the CEO by column. And from looking at series, I also know that I can access a particular item within a series using a row label. In this case, the labels are just the integers 0, 1, 2, 3. So I'll use the row label 2, and that's going to get me this cell value of false. As an alternative, if I say f1.loc 2, that accesses the row 2, and within that row I can access a particular item using its label, CEO by in this case. That gets me the same cell. I'm just using the row first and the column next to get at it. As a convenience, since we're accustomed to accessing spreadsheets using row, comma, column notation, I can just use one set of square brackets following .loc, and I can specify the row label and a comma and the column label. All right, so f1.loc 2, comma, CEO by would probably be the most common way of accessing that particular cell. But in fact, all three of these are equivalent. Okay, so what do we know? We know how to create a data frame. In this case, we used a dict. We can also read in a data frame from a file and create data frames in various other ways. We know how to access columns of a data frame as series. We know how to access rows of a data frame as series. And we know how to access individual cells within data frames. Now, if we want to add an additional column to a data frame, that's as easy as adding a key value pair to a dictionary. We say data frame sub, and then our new column name, PE ratio in our case here, gets. Now here we can specify a scalar if we want all of the rows to have the same value, or we can specify an iterable if we want the different rows to have different values. Let me specify a scalar here, 20.5, and that will make the PE of every one of our stocks 20.5. Of course, this is artificial, but let's just see that it works. All right, so that I have added my new column, PE ratio, and for the 4 rows representing the 4 stocks, A, B, X, and G, I have a PE ratio of 20.5. I can instead specify an iterable of the correct number of values. This time I'm going to say F1 sub PEG ratio. That is the price earnings to growth ratio.
And I want to have different values for my 4 different stocks. So I'll say 1.7, 0.9, 2.2, 1.1. I have specified these in a list. I'm just used to using lists. I could have specified this in a tuple. Once again, I have added another column, the PEG ratio, with the values that I gave, 1.7, 0.9, etc. So that's how to add another column. Now, if I want to get rid of a column, I can delete a column using del in the same way that I can delete an item or a slice of items from a list or a particular key from a dictionary. I'll say here delete del F1 sub and then my index P/E. I want to get rid of that PE ratio column. And sure enough, I have eliminated that column. So I know how to add and delete columns now. If I'd like to be able to add a row, that's also easy. I just need to remember to use loc so that I don't accidentally, in this example, create a column whose name is 4. I'm going to say f1.loc 4 gets, and then, well, just for gags, let me use a tuple this time just to prove that it works. So I'm adding a new stock whose ticker is Z, whose CEO by characteristic is true, whose return percent is 8.2, and whose PEG ratio is 1.3. And sure enough, we have successfully added that row with label 4. Notice that that row wasn't given a 4 just by default. I had to actually specify that I wanted 4 as the row label for that row. If you are adding rows to a data frame and you make some kind of mistake with the data types of any of the column values, including the row label itself, this is going to cause you quite a mess because of the problem of upcasting. Here I'm going to make a copy of F1. F1C is going to be F1.copy so that I don't destroy my original F1 in showing you this example here. If I say F1C .loc sub .5, now that's okay. This is going to create a label for a row of 0.5. But the existing labels are all integer values, 0, 1, 2, 3, 4. So by adding a floating point value as a label, all the other row labels are going to be upcast to be floating point as well. And if I now say something like 12, I want all of the column values here to be 12. Well, here again, this is going to create a problem, at least with the Boolean column. Let me hit the enter key and we'll see what we have here. F1C now contains, notice that the rows are all floating point numbers now. The ticker has been converted into a string containing 12. But the Booleans have all been converted to integer values by upcasting. So where I used to have true, now I have 1. Where I used to have false, now I have 0. And I've added a 12 at the bottom of this column. The 12 was simply converted to floating point to be of the correct type to go into the return percent and PEG ratio columns. All right, now you might wish that, oh my gosh, you've discovered that you've made this blunder. So let's see if we can just delete this row that we added by mistake, f1c.loc 0.5, and have everything go back to normal. Well, rats. Okay, so del works for columns, doesn't work for rows. If we want to get rid of a row, we have to use the .drop methods. So here we're going to say f1c dot drop 0.5. Will this work? Well, for one thing, the dot drop method does not actually directly modify f1c. What it does is to return to me a new data frame based on f1c with that row with the label 0.5 dropped. All right, so f1c itself has not been modified. And notice the problem with the data frame that was returned. My labels have not returned to being integers. My column under CEO by have not returned to being booleans. So I guess the lesson here is just don't make mistakes and you'll be all set.
Easier said than done, of course.
All right, well, fortunately, we still have F1 itself that is not destroyed. So if I display F1, I see the original data frame that I had. Okay, so we've taken a look at columns, rows, accessing, adding, deleting. Next up, let's take a look at slicing and indexing within data frames. This is going to be very familiar from what we've already seen about ND arrays and series. And to make these examples relatively easy to look at and describe, I'm going to create a somewhat less complicated data frame. We'll start out by creating a ND array, A12, which is just going to be A range 12. All right, so that's a one-dimensional ND array of 12 items. And if I say A12.reshape 4,3, we know that that's going to return to me a new two-dimensional 4x3 ND array. A12 itself is not modified by doing the reshape. I can use that reshaped A12 as the data part of a new data frame that I'm going to create. So this is going to be F2, and it's going to be pd.dataframe A12.reshape 4.3. And I need row labels and column labels. The row labels are going to be given by index and some iterable of row labels. I'm going to be very clever and original here and call my rows R0, R1, etc. I'll be back to you in a minute. And I'm going to be similarly original and clever and call my columns C0 through C2. Okay, so here we're going to create a data frame from a two-dimensional ND array and specify the row index as well as the column labels. And there is F. All right, well, I meant to call this F2, but that's okay. We're going to say F2 gets F1.copy. And if I need the original F1, I'll come back and put it back together. Okay, so if I say F2 sub and a column name, like C0, I get that column as a series. If I say F2 dot loc and a row label, I get that row as a series. Now, if I say F2 mod 3, that's actually going to give me back a data frame in which the cell values are modified to the mod 3 of their original values. Now, that doesn't change F2 itself. It just gives me back a modified copy of F2. If I compare F2 mod 3 with 0, this will give me back a Boolean index. Okay, so we can see here that column C0 is strictly integer values divisible by 3, and so I get true back for each of those cells,
and false for all the other cells. And surprise, surprise, I can use that Boolean index as an index within F2. So if I say F2 sub F2 mod 3 is 0 and times gets 2, the upshot is going to be that the first column, which is the column that is evenly divisible by 3, is going to be multiplied by 2. And this does change F2. All right, because I said F2 sub that Boolean index times gets 2. And so everywhere where the Boolean index was true, those values are getting modified to twice their original value. All right, so that's a Boolean index. Here we have a slice, f2.loc. We're slicing on the rows. R0 colon R2. Now, remember our Apple and Cisco example a little bit ago. If you give names rather than integer values as labels, the slice is going to be up to and including R2 rather than up to and not including R2. So this is going to give me a copy of F2, but only up to and including R2. So I've got the same number of columns with the same labels, but only the 3 rows, R0, R1, and R2. Now you can use integers to ask for your slice, and as a convenience here, you don't need to use the .loc, although frankly I find that an inconvenience myself because I always forget. Okay, so here we're saying F2 sub 0 colon 2, and since I'm using integer subscript here instead of named labels, now the meaning is up to but not including the sub 2. So I've only got the first 2 rows of F2 rather than the first 3 rows that I had previously. All right, so we have a lot of flexibility about how to access rows, columns, and cells within a data frame. The typical notation that one is used to from things like Excel is to give the name of the data frame and then the row and a comma and the column. If we use .loc as we've been, then we use labels for rows and columns. We can also use iloc instead if we'd prefer to give integer values to represent row and columns or row and column ranges. So if I say, here's F2, if I say F2 dot loc and then I say R1, this gives me all of the columns for the row R1. Whereas if I say F2.loc R1 comma C0, let's say, I get just the column C0 from the row R1. Okay. Now, I can do slicing. F2.loc R0 colon R1. And because these are named labels, remember that means up to and including. So this is going to be all columns, row 0 and row 1, R0 and R1. Or I can say F2.loc R0 colon R1 comma, and then some columns. Let's just say column 0 is all I want. Okay, so I've got from row 0 up to and including row 1, R1, but just column 0 in this case. That's a slice. Now here we have a fancy index, so-called, F2.loc square bracket, and then in another set of square brackets, I can specify the order in which I want these rows to occur in the returned result. Okay, so this time I want to see all of the columns of row 3 followed by all of the columns of row 1. And so I have R3 followed by R1. And as before, I could ask for maybe just a particular column of those two rows. Now, iloc, on the other hand, allows me to specify integer values as row and columns instead of names. So f2.iloc2, let's take a look at f2 again. f2.iloc2 is going to be just this particular row, row sub 2, and sure enough I have 12, 7, and 8 as the values with labels C0, C1, C2. Or if I want to do a slice, f2.iloc1:3. Now here, because these are integers, not names, this means 1 up to but not including 3. So I'm going to get row R1 and row R2 from this. And then finally, here's another example of a fancy index, 3, 2. This is going to be all columns from the row sub 3, that's going to be R3, and followed by the row sub 2, that's going to be R2. And I can combine my row selections with column selections, either individual columns or fancy columns or column slices, or here I have fancy indexes for both the rows and the columns. Let's take a look at that one, because this one is different from what we saw with endy arrays. I don't know if you recall that with endy arrays, when I used a fancy index for the rows and a fancy index for the columns, what I got back from an endy array was just a sequence, a one-dimensional endy array with item sub 0, 2, followed by item sub 3, 0. So I would end up getting back a one-dimensional endy array with just those two cell values. Sub 0, 2, all right, so sub 0, 2 would be this guy, the 2, and sub 3, 0 would be this guy, the 18. But that's not what I get for a data frame. What I get for a data frame is 0 sub 2, or sub 0 sub 2. Let me try this yet again. Row sub 0, column sub 2 as sort of my upper left-hand corner, and row sub 3, column sub 0 as my lower right-hand corner of a two-dimensional portion of that data frame. Okay, so let's see what we got here. So sub 0 sub 2, all right, so row sub 0, column sub 2, that's this 2. But I'm also going to get sub 0 sub 0, which is the 0. So that's my first row, is the 2 and the 0. Then my second row is going to be 3 sub 2. That's 3 sub 2 is the 11, followed by 3 sub 0, which is the 18. And so that's what I get there. All right, so in other words, I'm not getting a one-dimensional list of values. What I'm doing here is I'm getting a two-dimensional set of the combinations of these rows and columns. All right, well, I think that's enough fun and games with accessing individual rows and columns, slices of rows and columns, fancy indexes on rows and columns, Boolean indexes, etc. Let's turn our attention to taking a look at arithmetic with data frames a little bit more. I've got my data frame F2, And we know that if you try to combine together by addition, division, subtraction, what have you, two data frames that don't have exactly the same shapes and exactly the same row and column labels, that you end up with these so-called missing values. We saw that in the case of a series, a one-dimensional data set. Let's take a look at what's going on with a two-dimensional data frame. All right, so here's F2. If I say F3 gets F2.copy, at this point, F2 and F3, they're different objects, but they contain the same values. And so if I say something like F2 plus F3, I get back from that a data frame of the same shape, the same rows, the same columns, and the cells are all basically double because the two data frames are identical at this point. But let me try changing F3 a little bit. First of all, let's change F3 to have a new column, C3. And in F3, notice that there are 4 rows, so if I'm going to add another column, I'd better add 4 values, unless I want to add a scalar. So let me add 1, 3, 5, 7 as my values in that row. So here's the modified F3. Now F2 and F3 are no longer the same shape. And to make things even a little more different, let's try dropping row 1 from F3. Now if I just say F3 dot drop R1, that returns to me a revised copy of F3, but it doesn't actually modify F3. So I also need to say F3 gets F3 dot drop R1. And now I have F2 containing 4 rows and 3 columns, F3 containing 3 rows and 4 columns. And although there is overlap among the row labels and the column labels, there are also differences in both. So now if I say F2 plus F3, well, there is no row R1 in F3, so that whole row gets filled in with not of numbers. There is no column C3 in F2, so that whole column gets filled in with not of numbers. Otherwise, I do get the correct sums for the values where the row labels and the column labels exist in both. It's often the case that you'll have two data sets that are very close to the same kind of shape or organization, but not exactly the same. And it may be that you can simply specify some kind of fill value to be used in the case where data is missing from one or the other of the two data frames. However, I want to be clear here that if data is missing from both the data frames, the fill value is ignored. So let's take a look at this idea of a fill value. Now, I have to use the named add method here rather than symbolic plus sign. I'm going to say f2.add f3 comma fill value is 0. Now this does not modify either f2 or f3. It returns to me a copy of the sum of these two data frames using a fill value of 0. This item here, row sub 1, column sub 3, well, if we look at the original data frames, that cell doesn't exist in either one. In F2, there is no column 3, so there clearly is no row 1, column 3. And in F3, there is no row 1, so there's clearly no row 1, column 3. Since row 1, column 3 is missing from both, when I add those things together, I get not a number. I don't get 0 plus 0 is 0. Whereas for these other missing values, where I do have one value in the column C3 and F3, and I do have one value in the row R1 in F2, I do use the fill value of 0 there to complete the addition. Okay, so sometimes that will help you out of a jam if you have missing data in one data set or another, and you feel that it's appropriate to just use a fill value as some kind of default. If you have a data set and you discover that its rows or columns are not sorted according to their labels, you can sort the rows using the sort index method, or you can sort the columns using the sort index method with the keyword argument axis equals 1. Here, we're creating a data frame named F4, and you can figure out how that's being done. I'm going to just hammer it in here. All right, so I've got this thing typed in. Basically what we're doing is we're grabbing the data from our F2 data frame, and we're creating new row labels and new column labels that happen not to be sorted alphabetically. To sort the rows, we can simply say F4 dot sort index. Now, that doesn't actually modify F4. That simply returns a copy of F4 with the rows sorted according to their labels. F4.sort index axis equals 1. On the other hand, we'll sort the columns. Another keyword argument that you can use is ascending. Ascending is true by default, but if I say F4.sort index ascending equals false, you'll end up with the rows sorted in descending string order, so DCBA. And since what's returned there is itself a data frame, I can add another dot sort index, let's say axis equals 1, so that what I get is the rows sorted in descending alphabetical order and the columns sorted in ascending alphabetical order. Another facility that DataFrame provides is the ability to compute summary statistics. Recall that the NumPy module provides us a random submodule that contains a variety of random number generator functions. If I set the seed of the random submodule to 1, I'll be guaranteed to get the same random numbers as I have in the notes here. So I'm going to say A5 gets np.random. Rand_n is how I get standard normal random draws. I want a 3x3 ND array, and I'm going to round that to 3 places. So A5 looks exactly the same as what I have in the notes. And now I'm going to create a data frame from that, pd.dataframe. And I will hammer away and get back to you. All right, and I couldn't resist using a couple of comprehensions, even though it's probably more typing than if I had just manually typed these things in. So I'm creating the row labels and the column labels automatically here. And there we are. So I've got this data frame F5. If I ask for F5.sum, that's going to give me the sums of all the columns as a series. F5.mean will give me the means of all the columns as a series. F5.var for the variances. And if I say F5.describe, I get a collection of
descriptive statistics, count, mean, standard deviation, minimum, maximum, and then the quartiles, 25, 50, and 75%. Okay, so we have just barely scratched the surface of data frame. There's an awful lot more to this, and you will see more of it in this course and also in lots of other courses that you take in the program.